All right, so he will share his screen, and all of you, you need to be attentive and ask questions, because remember, some of you need to ask questions, and Becca is going to keep track of who's asking what questions, okay? All right.
So just a kind of background from what I did before. Integration, it's the area underneath the signal, and the values that are given for the integration is the relative number of protons for that specific proton. So let's say we have like a methyl group, and that'll show a signal on the spectrum. Well, based on the magnitude of that peak, it'll show that that's directly relative to the number of protons on that methyl group. So then here you can see the spectrum up top, and from there, like we did before, this is the example I gave before. What we'll do first is we'll look at the integration numbers here, and we'll find the smallest one. The smallest one is 27. And then we'll divide each of the integration numbers by the smallest one. So you'll see here 27 divided by 27, 40.2 divided by 27. And we'll get these values here. And since they're in a decimal form, what we want to do is we want to get them in a whole number form. So from there, we're going to multiply these numbers by 2. So we're going to multiply 1, 1.49, 1.05, and 1.56 by 2 to get whole numbers. And from there, we get a ratio of 2, 3, 2, 3. And this is the ratio of how many protons of each peak is relative in the compound. So it's a ratio of 2 to 3 to 2 to 3. And these step curves here is another representation of the ratio and the area underneath the peaks. Like I said before, just the step curve is just a direct representation of the ratio and the area underneath each peak. So for example, let's look at this compound here, 3-pentanone. From this compound, since it's equivalent, and that means it's symmetrical, there's only 2 kinds of protons. There's a methylene and a methyl. And from here, we can look at the NMR spectrum, and we can find the smallest integration number. So the smallest one will be 32, or 32.5. So we're going to divide each of these numbers by 32.5 seen here. We'll get 1 and 1.48. Therefore, we're going to multiply each of these numbers by 2 to get a whole number, and our ratio is 2 to 3. And luckily for this example, the molecular formula is given. So there, we can compare the ratio to the number of protons found in the actual compound. So there's 10 protons. So we can conclude that there's 4 of one kind and 6 of another kind to equal 10, because it follows the ratio as well.
Right.
And
any
then
questions? Sorry, any questions? You remember the methyl, the methylene, and the methine? I think Jamie talked about that when she did the presentation, right? Okay.
I have a question.
Yeah.
Okay, so you were talking about area underneath peaks and stuff. So I remember I kind of talked about something similar to that in my gas chromatography presentation. So
Sure.
is this also similar to that, in where you're using like integration values to account for like sensitivity in your equipment?
You do, but who did the presentation? Was it Jamie again, or was it Rebecca? I don't remember. So you have what is a 60 megahertz machine, and then you can have, 200 or 300 megahertz and so on. So I don't know if I'm answering your question. The resolution will be better, but where the peak falls for a particular type of hydrogen, that's not going to change. Does that answer your question?
Yeah.
So we're not too, I mean, the intensity is depending on the machine. That's that intensity is what is given on the bottom as the integration values.
And also the intensity of each peak is also directly related to how many protons are present.
Mm-hmm.
So that's kind of what we're talking about, like this integration number. So if you see a higher integration number, that means it's going to be a stronger peak, a stronger signal.
Mm-hmm.
Okay.
Does that explain? So in some ways it's similar, but in many ways it's different from the gas chromatogram. Does that help, John?
Yeah. Yeah. I kind of just heard like like similar terms being used, so I was kind of
Mm-hmm.
like,
Yeah,
I kind of thought they were the same, but
they are
yeah, that helps.
slightly different. Yeah. Okay.
So moving on, multiplicity, and this is just simply how many peaks are found at each signal. So you can have a wide variety of peaks, as you can see here. And the number of peaks in a signal is based on how many protons are next to it. So how many neighboring protons are affecting that type of proton. And this effect of splitting of each signal, so what causes this is called coupling. So when I'm talking about neighboring protons, let's look at HA here. The neighboring proton that's going to affect HA is going to be HB. And therefore, since there's only one proton affecting it, that means it's going to appear as a doublet. It's going to have two peaks. And I think I went over this before, but it follows the N+1 rule, where you take the number of neighboring protons that are affecting it plus one, and that's how many peaks you're going to have.
Okay, so I'm going to say something here, just repeating what he said. So if you look at this structure that he has, there are only two protons. So the others are blocked off, which means there are no protons there, and we're not worried about those substituents. So HA is going to be influenced by HB. So HA normally will give one peak, but if he has a neighbor, he will give the number of neighboring hydrogens plus one peak. So he has one neighbor, so he will show up as two peaks. Okay, so do not include him. You look at his neighbor, how many neighboring protons there are, and you add one to it. And so he has one neighbor, so he will show up as a doublet. Does that make sense?
We'll look at other compounds too.
Okay.
So here, what causes this effect of how many peaks is magnetic effects. So what's going on is these protons can either align with or against the magnetic field of the other proton that's affecting it.
Okay.
And if you look, yes.
Let me set this up for them. So here, there's an example of a case where HA is near two protons, right? So if HA is near two protons, you look at the screen to the right, you see three peaks. So if you have two neighbors, it'll show up as three peaks. So Hutch is trying to tell you, and also if you look at the three peaks, a triplet, you will see the peak 1 and peak 3, they are of the same height, but the peak in the middle is taller. So he will now explain why the triplet is of the shape that you see on the right.
So when it has two protons that are affecting it, it'll cause a triplet like shown. So there's three possible ways these protons can align with the neighboring protons. The proton can align with the field, it can align against the field, or it can align one with and one against. So, and the reason why the one with and one against is bigger and taller is because it can align with one and against the other, and then it can flip. It can align with the other and against the opposite one, if that makes sense. There's two possibilities of lining with one and aligning against one.
Mhm.
Whereas if it aligns with both of them, there's only one possibility. That's why it's shorter.
Yeah.
And going back to this slide,
Mhm.
so if HA is affecting HB, HA and HB can only align with each other or against each other. So there's only two possibilities. Therefore, it appears as a doublet
Okay,
because there's only two possibilities.
okay. So Hutch, the doublet here is because of the HB pointing up and the HB pointing down.
Okay.
So that's why you get the doublet.
Okay.
Okay. So here you look, if you look in that picture, it's only the HB protons that are shown. So it's only the neighboring protons that are shown.
Right. So like I said before, the n+1 rule, where n equals the number of neighboring protons. So let's say there's 3 neighboring protons. And then n+1 rule, 3 + 1, 4 peaks. It's pretty simple, and this will be seen for most of the NMR spectrums that you see. And this table here is just from before with the magnetic effects. It just shows how the peaks will appear if you have like a doublet, triplet, and on. So let's see if I can rearrange this. So the relative intensities, so a doublet, 1 and 1, therefore they're going to be the same height. A triplet, like you said, like you saw before, you're going to have a 1, 2, 1, where the middle one is taller because it's a higher intensity, and then and so on. So you can look at this chart and see how they're going to appear on the graph or on the spectrum. Some rules to remember. So protons that are equivalent to each other do not affect each other. So let's look at this compound here. These protons, the two sets of protons are equivalent to each other because they're the same type of proton. Therefore, they can't affect each other. So this is two methylene groups, right?
Mm-hmm.
So since they're two methylene groups, they can't affect each other. Well, if you had a methyl group on the bottom and a methylene group at the top, they would affect each other. And for splitting to take place, the proton should be 2 to 3 bonds away. So, and what I mean about this is look at the first where it says splitting is observed. If you look at the first one, HA, if you go along the sigma bonds, it's 2 bonds away. And then if you look at vicinal, HA is 3 sigma bonds away from HB. So splitting, you will see splitting there. So you go to the last one, the third picture, and you see HA is 1, 2, 3, 4 sigma bonds away. So we can say that this is too far away from each other. These two are too far away from each other to affect each other.
Okay, so this is important. So like he said, if you look at the adjacent carbons, and sometimes you'll have carbons on both ends. You look at the adjacent carbons, this side and this side. So your neighbor to the right and your neighbor to the left. And if they have hydrogens, those are the neighboring hydrogens. If your neighbor's neighbor has hydrogen, those will not affect the splitting. Okay, so it's very, very important to know this.
So N+1 rule only applies for equivalent compounds. So the one you see on the left, even though these two groups won't affect each other, this is an example of an equivalent compound. It is symmetrical. So that's where you see the N+1 rule. And the one on the right is not equivalent because it's not symmetrical. So you won't typically see the N+1 rule there.
Okay, so he'll be looking at examples, and I think it'll become more clear at that time.
Okay, so we can also look at the distance between each peak, and these are known as J values, or you can call them coupling, or what is that?
Coupling constants,
yes.
yeah. Now, just a second for everybody watching. This, the one in the blue, see how that relates to the structure on top. I don't think you can see my mouse because Hutch is sharing the screen. So the CH2 group, the methylene group, is split because of the blue hydrogens. You see that? So the two HAs are not taken into account when it comes to the splitting. So these blue hydrogens are responsible for the 4 peaks that the methylene group shows. Now look at the one on the right, the red one. You see a triplet. And do you also see the ratio 1 to 2 to 1? Look at the heights. And where is this coming from? So this is the peak for the methyl group, but the splitting is due to his neighbors. See that? So you are responsible for the chemical shift where you are on the x-axis, but your neighbors are responsible for you splitting up like this. Do you understand? So the peak itself is indicated by the value of the chemical shift on the graph, but how they split is because of their neighbors. Okay, so keep that in mind.
And the J values, so when you look at this picture, you see the JAB, so that's the J value. And these J values will be equal for neighboring protons. So you'll see each J value, each of these will be equal to each other. And then separate from that, these two will be equal to each other.
Yes.
And then J values can be found anywhere from 0 to 20 hertz, and they're dependent on the type of type of proton found in the compound. Okay. Like she said before.
Yeah. So the J values, you will not be able to see that in the spectra that we gave you. Okay. So, or it may be very difficult for you to experimentally calculate that. So this is more of a theoretical spiel at this point in time.
Complex splitting. So this is where we left off last time. Mm-hmm. So this is when you see a proton or a group of protons that are affected by two groups, two sets of neighboring protons. So look at the picture, and the group HB, those protons are affected by both HC and
Mm-hmm.
HA.
Mm-hmm.
So when you think about it, because of the N+1 rule, HB will split into a quartet and a triplet theoretically, because that's that HC will cause HB to split into a triplet, and HA will cause HB to split into a quartet. But since it's complex splitting, since it's both of them having an effect on HB, we will take the 4 peaks and multiply it by the 3 other peaks, so the quartet and the triplet. We're going to multiply them to get a total of 12. So it's going to show up as 12 peaks since both of them are affecting HB.
Okay, that's right. So like he said, I'm just repeating if that's okay with Hutch.
That's fine. That's fine.
Okay, so if you did not have the HA, HB will split as a triplet. And then if you did not have HC, then HB will split as a quartet. Then we would think maybe the quartet and the triplet, you should add them to get the composite splitting. But actually, it's a product. So it's 4 times 3, and it gives you 12 peaks. And I would say anything above 6 peaks in the spectra that you get, it'll all be so close to each other. So you will call those as multiplets. But theoretically, if a question is asked, for a problem like this, then you'd have to say you should get a total of 12 peaks for HB. You'll see that? Okay.
Cool. So here, the signal also depends on the J value as well. And this is more concept, like she said before, because we won't see J values on our spectrum that we have for our post lab. But just keep in mind, if the JAB value is bigger, so that's the value of HA and HB, then the signal will show up as a quartet of triplets. So there would be 4 signals, and they'll all be triplets.
Hutch, just a second. So remember we said 4 times 3, that's 12. So this is the 12 that we're talking about. Okay, so if you can zoom in closely, the next slide. So you're supposed to see 12, right? If you zoom in closely, this is how you would see it. So you have 4 times 3, that's 12. So this is how it will be. And sometimes you will get 4 different peaks, each is being a triplet, or he's going to tell about the next case where you will have a triplet of quartets. And when you get each, when would you see a quartet of triplets? When will you see a triplet of quartets? That depends on the JAB value.
Yes. Okay. So now the JBC value, if that is bigger, then you'll see a triplet of quartets. So you have 3 peaks, and it'll have, or 3 signals, and they'll all have 4 peaks. And most of the time, like on our NMR spectrum, it'll be so close together, and it'll be so bunched together that we'll see a multiplet. And we probably won't see 3 distinct peaks if this were the case, but we'll see something more like this, where it's all bunched together because it's so compact on the paper. And some signals for some known functional groups. So an alcohol functional group, they typically range from 2 to 5 ppm on the NMR spectrum, and this will appear as one single peak. And it'll be relatively strong, a relatively strong peak. So in this spectrum on the bottom, if you'll look at the middle peak, it's just a single peak. That is the peak given off from the hydrogen in the alcohol group. And then for aldehydes, you'll see a single peak as well. And this is typically around 10 ppm. And this will be good to know in the example that we do later that I show you too.
Okay. So can you go back to the previous slide, please, Hutch? Okay, so this one, the complex splitting, you have to know for theoretical purposes. So you will not be asked to analyze something like this, but you need to know how complex splitting occurs theoretically. So it could be a question on the exam, on the quiz. But the next one, the next slide, Hutch, if you have an OH group, even if the OH group has neighboring hydrogens, I think Hutch will talk about it later, I'm not sure. But this OH group will always appear as a singlet. So he's a special kind. And where will he be? He'll be anywhere between 2 to 5. So, and he will always appear as a singlet because he is not going to be affected by his neighbors. So in a way, it'll be easier to identify him because he's a singlet, or sometimes you'll have to identify him at the end, okay? Either way, he's very unique. Another one is the aldehyde. You think of the aldehyde functional group, CO, double bond, right? Carbonyl. And to one side, you have the hydrogen. So that hydrogen also does not have a neighbor. And he appears a lonesome guy around 10 ppm, okay? So any of you, if you have your unknown NMR and if you see a peak around that region, hey, okay?
Yeah, it's really important to remember this because it makes identifying compounds a lot easier. Because if you see a peak around from 2 to 5 and it's just a singlet, you can automatically look at that and say, hey, I think there's an alcohol group in here. Or if you see a singlet at 10, you can go, hey, I think there's an aldehyde in this compound. So it's important to know this because it makes it easier on you.
That's right. But remember, the OH group sometimes can be misunderstood for a methine group with no neighbors, okay? So it could be a methine with no neighbors or an OH group. But if the OH group is further down, like close to 5, then it's more likely to be an alcohol than a methine group, okay?
This is my example.
Okay, you're gonna do that later, right?
Yes.
Okay. Do you want to simply go over some of the features since Michaela is not out of class yet? Unless somebody has questions. I think Michaela, who's going to talk about that OH group? It was not in your section, right?
No, it wasn't.
Okay. This is I'm pulling out the textbook.
I had a question. Can you go over the JAC,
Values, yeah. Okay.
JAC, whatever that is, the quadruplet something, because I did not understand.
So when we're looking at the J values, especially for this compound here, so when I'm talking about the JB value here, this is the splitting due to HA on HB.
Right.
And then for the BC value, that's for HC affecting HB. So,
okay. But those values we don't have to find ourselves. The machine does it for us, technically, or something.
Yeah. If we have a bigger machine, yeah, that'll do it for us. And even our machine can do it, but we didn't particularly look for it.
And that's And you compared those two values, and that's when you are going to come up with a conclusion if it's going to be
Quartet of triplets or triplet of quartets.
right, depending on which one is bigger.
Yes, yes.
So if HA or J value of AB is bigger,
Uh-huh.
so if HA, if that was the only thing affecting HB, it'll appear as a quartet, right?
Right.
So if HA is big, or if J value of AB is bigger, just think you'll still have 4 peaks, but you'll have triplets as each peak.
Because of the other group that produces triplets.
Right.
Mhm.
Right.
Right. And if BC is bigger, you'll see, so if HC was the only one there, you would see it splitting as a triplet, right?
Right.
So you will have 3 peaks or 3 signals, and each one will have quartets because of the other HA.
Okay.
Does that make more sense?
Yeah.
Okay.
Any other questions? Hutch, didn't you have the ethyl propyl, or is that coming up next? Remember the ethyl
I thought I had it.
isopropyl? Did you skip those?
Maybe. Here, let me take it off of
Yeah,
screen
yeah,
there
yeah.
and look at my original PowerPoint.
Okay. It's on, I put it up on Canvas too. Pattern recognition. Everybody doing okay? Other than Shelby, anybody else working outside the home? No. Oh, no, Shelby works at the pharmacy. He's going to check his PowerPoint because there's some slides that he needs to talk about.
Which PowerPoint is it on Canvas?
It should say your name, Hutch. Go to
Oh,
chapter
I
15.
have on.
Okay.
That's the one I had up.
That's
I
what
guess
you had up?
Yeah, I guess I didn't have those slides.
I didn't put those.
I can look at the book right quick though.
No, you should have it in the one you sent me last night, the latest one.
Mm-hmm. Okay, yeah. I don't know why it didn't come up
Yeah.
on PowerPoint.
Hey, look at Shelby's doggy. Oh.
Do you want me to share my screen from Canvas?
Yeah, yes.
Okay.
After coupling constant, you had pattern recognition and then complex splitting. So you did the complex splitting.
Right. I don't know why it didn't come up on mine. That's weird.
Yeah, yeah. And you had the proton as well, but I don't think I saw it on your PowerPoint, but that's okay.
So commonly known NMR spectrum patterns, ethyl groups, isopropyl groups, and tert-butyl functional groups.
Can you
So,
make this bigger?
let's see.
You may have to download or Zoom. Yeah, great, thanks.
Is that better, or do I
Yeah.
need to go a little bit more?
No, this is fine. I think it's fine. If somebody has a problem, let us know. Yeah, there you go. Now, this is very important because you can tell if your compound has a CH2, CH3, you know, next to each other, which is an ethyl, or does it have an isopropyl or tert-butyl? So this is very useful, just like the aldehyde and the OH chemical shifts.
Mm-hmm. So the ethyl group, if you look at the first picture here, ethyl groups will show a triplet upfield, which is to the right, and a quartet downfield, which is to the left. And this is because this ethylene group is affected by these 3 protons here, which will make it show as a quartet. And then the methyl group is affected by the methylene, these 2 here, which will make it show as a triplet. So just, that's common. That's what you'll see for an ethyl group. Isopropyl groups, you're going to have a doublet upfield and a septet downfield. And this is because the 2 methyl groups here, they're the same group, so they won't affect each other. But this single proton here will affect it, and the 2 methyl groups will affect that single proton. So these 2 methyl groups, since it's only affected by 1 proton, it'll have 2 peaks, and that'll be upfield. And because there's 6 protons present, the intensity of the peak will be relatively high. And then this single proton here, it's affected by 6 other protons in the 2 methyl groups. So it'll appear as a septet. And it'll be really small because there's only one of that specific proton. And then finally, this tert-butyl group here, it'll only appear as a singlet because there's not a neighboring proton affecting the 3 methyl groups. So there will only be 1 peak. And since there's 9 of these protons, so there's 3 methyl groups, 9 protons total, and that'll make it have a really strong signal because there's 9 of those protons present. And then I think that's it until the example.
Example, okay.
Mhm.
So I want to show them something before you do the example.
Okay.
I wanted to look at, if you have your 3rd edition book, I'm on page 677, but I'm going to show it on my camera.
Are we going to wait for Michaela before the example, or do you want me to do it before?
Yeah, okay, it's saying that you have to start the meeting. Oh, okay. Let's see, I think she's here.
Okay.
Let me see. So you could wait. Is that okay, Hutch?
That's fine. Yeah. Do you want me to stop sharing?
Yes, please.
Dr. Mary,
Yeah, go ahead.
I
Shelby.
didn't know that this is going to be more than an hour, and I have to work at 1:30, so
Okay.
I'm going to have to hop off at like 1:15. Is Michaela's presentation going to be uploaded?
Yeah.
Okay.
And before you leave, Becca, could you help Michaela join the meeting, please?
You just want me to forward that email to her?
Yeah, she was on there before. Now she's saying that, so she's having trouble.
Okay.
All right. So this Friday, we are going to meet from 12 to 1. And starting next week, we will be meeting from 12 to 1, Monday, Wednesday, Friday.
Mm-hmm.
And next Tuesday, we'll meet again from 12 to 2. Because
So every Tuesday isn't going to be 12 to 2?
I'm going to schedule it. Next Tuesday, we'll use the 2 full hours.
Mm-hmm.
But after that, we may just do, it may be a problem solving session from 12 to 1 or so.
Okay.
But so everybody, and I'm going to post this on Canvas. Make sure that you are available 12 to 1 Monday, Wednesday, Friday, and 12 to 2 on Tuesday. That
Okay.
one may be a shorter one after next Tuesday. Okay.
Okay.
So then, if you plan your schedule, that's why I'm not having a class tomorrow, but we will have one on Friday. And the one on Monday, I was talking earlier, I plan to do a quiz from 12 to 12:30 or so, and we'll see how that works out. So you will be on Zoom.
Zoom.
On Zoom, and then I will send out the questions at 12, and you will print it out and then start working on it. And if you have any questions, you can ask me, and
Okay.
then you will upload it, and then we'll do problems or continue with lecture like we do in class. Okay.
Okay. And how is like our final going to work out?
So some of us, at the beginning we talked about like exam, how is an exam going to be? And final, I'm not sure. We're not there
Okay.
yet. And so I'm only thinking about how we're going to finish up the labs, and we'll do the labs, there'll be virtual labs like we are doing now.
Mhm.
We'll finish those off first, and then we will have quizzes like we usually do. Then I'd like to have one exam, probably not more than a total of 1 hour. And then we'll worry about the final.
Okay. I didn't know if we were gonna do it like on Zoom or if we were gonna do something with sapling or. Okay.
Yeah, so I'm looking at different options. So it could be a combination. So the final exam could be, 2 parts or 3 parts.
Mhm.
Because the mechanisms, they have to be handwritten. That's why the next quiz is going to be a handwritten one, because it's hard to do the exam. I mean, the mechanisms on Canvas. And I'm also trying to upload like a multiple choice exam or a short answer exam on Canvas. So I'm looking at different things, and I've never done that before. So it's a big, learning
Mhm.
process. So I'm going to do things like this. And I'm also asking like biochem instructors how they're doing it. And since Mr. Smith did it this way for his math classes, they were given the quiz or the exam, and they printed it out or wrote the question answers on a sheet of paper, and they uploaded it. So I want to try that for our mechanisms and resonance drawings, something like that. So we'll go step by step. But if you have any ideas, please let me know. I also looked at sapling, like have sapling timed, and then create a test on there.
Mhm.
So that has the drawing capability, right?
Yeah.
So that's an option. Now we are using the Wiley textbook, but we are not using Wiley Plus. And the Wiley Plus has, exam capabilities as well, but we don't have access to it. We didn't buy it. So that's the plan. So I'll post all of this announcement on Canvas after we are done. And I'm recording this, so that'll be posted as well. Now, and also they told us to take attendance for, they sent us an email yesterday saying that attendance has to be taken. And so if we have Zoom sessions, please plan on being here and participate, so that will count. So for the next few weeks until we hit finals week, we'll plan to meet on Zoom on a regular basis. Okay. All right. And now work on that homework as well. And if you have any questions, I'll be happy to answer those for you. I can set up, one-on-one Zoom sessions, or 2 or 3 can be there and we'll find times. Okay. All right. Okay. Any other questions? What's your doggy's name?
I'm sorry. Do you
Yeah,
know?
Carly. Go
Do
ahead.
you know if the testing center is still open? I was just there last week to take up an exam I was gonna take when we came back from spring break, and they said they're gonna stay open there as long as possible. I know
Yeah.
that's like a pretty small class. So I know they are planning on staying open as long as possible, but I don't know if that changed whenever they decided to halt the whole semester.
Yeah. Did you take any last week? I think last week they were open.
Yeah, I took one on Thursday.
You did? Okay. So could you email them and find out?
Yeah, because I know we're not like a large class, so even they're cleaning that area weekly and leaving it open, and they did have the room across the hall and the classroom next to it. So for I think maybe smaller classes, they'd be able to do that. But
yeah.
I'll email them and see.
Yeah, and let me know.
Open.
Yeah, and we'll talk, you know, over email and see how best we can accommodate. Okay. All right. All right. Any other questions? All good questions. Okay. So Michaela is waiting, right, Michaela?
Yeah, I'm so pumped.
Okay. All right. So, oh, I was going to do a little bit before you go on.
Okay.
So let me share the screen, and I'm going to do a little example like ethyl alcohol. How will it appear? And then I'll let you share your screen, Michaela. Okay, I gotta adjust this. Is it very blurry? Is that better? Okay. Now this is my spectrum, and this is ethyl alcohol. Okay. So if you have a spectrum and you're given the structure, you don't have the spectrum, you're given the structure, how will you draw the spectrum? Now, how many types of protons are there? That's the first question that you would ask. Protons. How many types are there? You have the methyl, right? CH3. I'm not set up for the document camera today. This, and then OH. All right. Now, just like Hutch, I'm going to label these as, I'm going to make that my C. I'll remove my hand and you'll be able to see it better. Okay. See that? That's OHC. So you have 3 types. That's the first thing that you'd have to look for. So on my NMR spectrum, I should see 3 signals. The OH, remember, it's unique. I would say this oxygen has this carbon as a neighbor, but he's unique and he doesn't get affected by anything. Now, in ethyl alcohol, which is what I've drawn, he's going to appear as a singlet. Now, by the way, if you don't like this, you can see this on page 677 in the 3rd edition. Okay, 677 in the 3rd edition. So this is my OH group. And he can be anywhere between 2 and 5. Okay, in this particular case, he's chosen to be at 2.1 or between 2.1 and 2.3. Okay, there's a range. Now, let's look at the CH3. The CH3 in your chart, okay, the NMR table that I had, it'll tell you where the CH3 appears. I'll pull it up a little bit later after Michaela's presentation. So the CH3 is going to appear at a certain range. And I've indicated the range here. Okay, it's not the best. Okay. Is it worse than before? Okay. Now the CH3 has how many neighbors? 2 neighbors. So how many peaks should we see? We should see a triplet. we should see a triplet. So this is a CH3 peak, and it's a triplet because he has 2 neighbors, and the neighbors split him up into 3. Now the CH2, I'm going to tell you, it's further down. So it's between 3.6. See, I have this region here. This is where your CH2 is going to appear. Can you draw the peak that you would get for the CH2? The CH2 group has how many neighbors? Would you count the OH? Do not count the OH, because the OH guy is unique. He doesn't get affected by anybody else, and anybody near him is not going to be affected by the OH group because he's never home. So the CH2 should be a quartet. And what's the ratio, Hutch? Do you know? Is it 1 to 3 to 3 to 1? Something like that. Okay. Do you see? So this is a typical spectrum. So here lies my CH2. And how do I know that the CH2 should be here? You get this from your table. Chemical shifts are given in your table. The CH2, a certain range. A CH3, a certain range. OH, like we said, anywhere between 2 and 5. Aldehyde H, close to 10. So in that range, you will show the splitting pattern. And so your alcohol, ethyl alcohol, should look like that. I'm sure it's shown better in the textbook. This is the spectrum for ethyl alcohol. What does a 3 tell you? That's the integration value. 3 protons, 1 and 2. So here's your CH2 quartet, CH3 triplet. The CH2 is not affected by the OH. The OH is not affected by the CH2. Got that? Now, where is the table? Somewhere in here, but keep a copy of that. Okay. And here is what Hutch talked about. If there is an ethyl group next to this CH3, you should see a CH2 and the same splitting pattern. If it's isopropyl, 6, and then the hydrogen. The hydrogen will be a septet, and this guy will be a doublet. You see, they're so close you can't tell really, but that's a doublet. And if you have a tert-butyl, just one big peak, 9 hydrogens, and a singlet. Got that? Okay. Oh, we let Michaela talk.
Do you want me to go now?
Yeah, please.
Okay. Hi, class. How's everyone doing? Good.
They were okay at 12 o'clock now. It's been enough.
Okay. Can everyone see the screen? Maybe?
Jamie says
Yeah.
yes. Yeah.
Oh, okay. Thank you. All right. I'm going to present now. Let's see. Where's the present
Somebody's-
button?
Okay, John's saying, yeah, he can hear. Okay.
Oh, wow. So good. Where's the present button? It's like blocked. Oh, wait. Found it.
You want to
Okay.
make it big? Yeah, thanks.
Wow. This is my same presentation from last year, so it probably has some cool transition stuff in there. So enjoy. Also, if you want me to make me I'll make myself the pin screen. But if you want to make me the main one, you click like the little dots I think, right?
Are you able to see her screen? Fill up your screen.
Or like maybe it's easy.
Jamie, yes?
Okay. Because I might use this whiteboard and draw out some things, but I think I should be able to do most of it while talking. Okay, so, oh, there it is. Okay, so now what we're going to do is there's two techniques we're going to learn. One is drawing the spectrum, and then the other one is looking at a spectrum and to be able to just identify the compound. So you guys have already talked about the chemical shift, the multiplicity, and integration. I think the previous presentations went over that. Does that all sound pretty familiar?
Yeah.
Yeah. Okay. So now we're going to use a combination of all of these three skills to do both of these things. So here's an example. This is one that we'll just go through. So I'm going to move this real quick.
This is a skill builder in there. I think it is. Let me check.
I think this is in your textbook. So I'm just going to walk you through it and talk with you guys out loud on how to do it.
Okay.
So the first thing that you want to do is kind of what Dr. Mary was talking about earlier, is you want to identify all the sets of hydrogens in the molecule, or protons. So of course you want to keep your eye out for equivalent hydrogens, as I stated right here. So if we look at this molecule, I think I go into it more into detail on the next slide. So you can look and see that first I just went through and I circled all the different hydrogens and the protons and where they were. So this one obviously doesn't have hydrogen because there's 4 bonds there, but we see we have this methyl group here that's near the carbonyl. We have this hydrogen right there that wasn't drawn in the structure, but you need to make sure that you're still looking for that. And then 2 other methyl groups right here. And in my presentation, I labeled these both as A because they're both equivalent. So they're both beta to this oxygen right there. So they're both going to have the same value, so we can group them together. So you guys have kind of already done this earlier, but that's the first thing that you want to do. Does that make sense? Sound good?
Mm-hmm.
Okay.
So what Michaela is doing, I did a rough graph for the ethyl alcohol. She's going to specifically show you where the chemical shifts are. And I think you did examples like that. We did examples like this before with Jamie, I believe. So she's going to review that.
Yeah. We'll see. Oh, wow. Okay. So first, I'm going to go through the chemical shift of, I think each, or let's see.
And
no, I'm going to go through the chemical shift, the integration, and the multiplicity of each signal. So I'm just doing it like one by one. So you just like, so first, I'm just doing this methyl group right here. Yeah. So if you look at that little chart that you have.
Mikhail, can you all pull your NMR table out so you'll have values for the methyl, methylene, and all that? Okay, so keep that handy. Thanks.
So this is the table that you guys have, or I'll wait till you guys go get it.
Yeah.
That way I don't rush.
Michaela goes like a bullet train, so I have to.
Yeah. Speed round.
Yeah. Please, please keep your table handy. It's on Canvas. It should say NMR table. Pull that out so you'll know how to do the problem. And get a snack or coffee or something.
Yeah. Or water. Water's good too.
Water's good, yeah.
Okay. Everyone. All right. So the first thing you want to do is you want to find the chemical shift of each proton group that you already identified. So I started with this methyl group right here. So if you look on the table, any methyl group has a shift of 0.9, but because it is alpha to the carbonyl group, you're going to add that value of 1 to it as well, which there's 3 special groups I think that you have on that chart as well. So as long as you can identify what groups it's near, you can find the chemical shift as you've already done previously. Then after that, I'm going to look and see what the integration value is. So there's no other equivalent hydrogens with this methyl group. So there's 3 protons total though, so the integration value is going to be 3. Pretty simple. Then the last thing is the multiplicity. So multiplicity occurs if there are neighboring hydrogens. So there's no hydrogens on this carbon, so it should be a singlet. There's no other hydrogens that are messing with the signal. So looking at this, we already have all the information that we need to draw this signal on our NMR graph. Now we're going to do the other ones. So, so now I'm going to do this hydrogen that I circled right there. So, there, I'll see if it loads. Okay, so again, we're just going to start with the chemical shift. So this is a methine carbon. There's only one hydrogen in the group. If you guys have the little table, you can identify the methine protein is only has one in its group. So it has a chemical shift of 1.7, but it is also alpha to this oxygen group. And it's alpha because it's right next to it. So that means that we're going to be adding 3, which again, you can find that in your table, giving a chemical shift value of 4.7.
So what functional group is that? Because you're adding +3. Oxygen of what group?
Are you asking me or are you asking class?
Yeah. Anybody? Jamie, what is that? Oxygen of?
Esther.
I don't know if Michaela knows.
Yeah, I forgot everything.
Yeah, that's right. She's just...
Okay.
Jamie? Okay, Jamie,
Yeah.
what is it? Oxygen of what? What functional group?
You said Esther.
Esther. Okay, all right. Thanks.
Good job, everyone. I mean, Jamie. So, yes, because it is alpha to the oxygen of the ester, we add 3. Now, next thing, integration. So, there's only one hydrogen in the group. There's no other hydrogens that are like this one. So, there's going to be an integration value of only 1. And then for multiplicity, there's no hydrogens over here, but there are 6 hydrogens right there, or 6 hydrogens combining both of these methyl groups together. And if you guys remember the n+1 rule, that means that since there's 6 hydrogens, I would do 6 + 1, making this going to be a septet, which is basically it's going to have 7 peaks. That's all it means.
Remember, the whole group is an isopropyl group.
Yes.
We just talked about that, right? So the proton, the hydrogen, will split as 7, and then she'll show you what happens to the CH3s.
Yes. Okay, and then the last one we have to do is the CH3 groups. And because they're equivalent, we can group them together and analyze them because they're both going to, like their signal's going to be together on the NMR spectrum graph that we're going to draw. So, I don't know why. Okay, so for the methyl groups, it has a chemical shift of 0.9. So just like this methyl group, but the only difference is that it is beta to this oxygen of the ester group. So remember, it doesn't add on the +3, it adds in, I think it's like, what, 1/6 of the value? Is that what it is? 1/5, close. So it's going to be adding 0.6 to that 0.9 to get a total of 1.5 ppm. So this is how you're going to, or you can do both of those together. And then the last thing, or the next thing is integral values again. So since we can group all of these hydrogens together, and there's 6 of them total, the integration value is going to be 6. Also, I don't know if I stated this, but integration, you guys already talked about that, but integration just means like the area under the curve. So if it's like 6, it means there's going to be like bigger peaks because there's going to be a lot more area under the curve. Or if it's like 1, it'll be like a lot tinier, which we'll kind of see that on the graph, and you guys have probably already seen that. And then the last thing is multiplicity. So these are both together. So that means like for this carbon, I'm not going to count these 3 hydrogens because I'm grouping both of these together. So the only neighboring hydrogen that's not in this group right here is this one. So since there's one neighboring hydrogen that's not in the group, it's going to be a doublet, again, because of the n+1 rule. Does that kind of make sense? Okay. So that's all. Now we just analyzed all the different hydrogens of this molecule, and we have all the values that we need to graph. So the next thing that we do is graph it. So this is a graph. I found this online. Obviously, yours will probably look a little bit more detailed because this one's, it's kind of hard to see this. But when drawing the graphs, all you want to do is just make a little spectrum here on the bottom. Remember, your highest values are usually around like 12 ppm. So just kind of make it to 11 or 12, and that should be good enough for your spectrum. And then usually what I would recommend when drawing these is that you can see I went through each hydrogen group like different or separately. So I would just sit there and be like, okay, I just got this chemical shift, integration, and multiplicity. I'm going to draw this one signal, and then kind of just like leave a little blank and then keep on adding more as you go. You don't have to do it all at once. So you can see that this matches up though. We have this one hydrogen, and
Michaela, can you show this on the board that you have, like with the actual
like draw it out for them?
Yeah, with the actual metal
Sure.
shifts you got.
I have a whiteboard, y'all, so I'm gonna, I guess, draw
You
it
have
out.
to switch to the video maybe.
Oh, how do you do that? I don't know how you do it.
Stop sharing.
Oh,
Yeah.
okay. I'm gonna go my PowerPoint though, so I can
Mhm.
look and see.
Yeah.
So I'll draw this first. So
Yeah.
I'll
You have
set-
them draw it too. Can you all draw a spectrum and then put the chemical shifts? I'm trying to see how to make yours look.
Okay. Yeah, so maybe start by just drawing the spectrum. Don't put any of the peaks in yet. Just do like from 1 to 11, and that's probably good.
Mhm.
And then we can work on it together. Okay. I think yours is still the main one.
Which one?
Aha! Now I made mine the main one, so we're good.
Okay. I
Okay.
see. Was it? Okay.
Yeah. So here's what I set up. I just set up a little, oh, I think it's backwards.
No, it's fine.
Oh,
Right.
okay.
Here
Oh,
it's,
maybe it's just backwards to me. I don't know.
yeah, it looks fine from my point of view.
So it's from
Yeah.
1 to 11, and here. So going back, so we had our first, I'll draw the compound up above too, right here, so that way you guys can see. Okay. Okay, so here's our compound up above. So now we're gonna draw all the signals again. So this is the one that I did first in the PowerPoint. So that's the one that had a chemical shift. Oops. It was, let me go back. I don't know what the exact value was, so I'm gonna double check it.
Let me see.
It's in my PowerPoint, but that one was 1.9. So usually what I would do first is, since that's going to be around 1.9, I'll draw like a little line here like that. And then it has integration value of 3 and it's a singlet. So, I mean, it's all just relative to how you make the rest of the graph. There's no like how high it needs to be. So I'll just probably do like right there. And then usually you draw like a little like 3 on top or something, I think.
Three
Like
hydrogen,
H,
capital H.
something like that. That way you signify that you put the integration value in there. And then for the other one, it was, oh, there's one at 1.5. Okay. So the other one was at 4.7. So that's like, we'll say right about here. And that one, and this, we're talking about the methine protein right here. Or proton, not protein. So this one has the integration value of 1, and then this one has the septet because it's near all of these hydrogens. So again, that's kind of really hard to do because that's like 7 little peaks. So just try your best to make a good amount of peaks, but you want it to be like pretty tiny. So mine is as best as you can go, and then just put 1 hydrogen.
Now, if you are asked to draw this, what I would do, Michaela, is expand, from 1 to 7, it's just.
Yeah, you probably have, a lot of times what they'll do is they'll have like something like up above where they'll like show that it's like 7 peaks or something like that. Like, I don't know. That's
Yeah. Even
but,
if you say it's a septet, I would understand.
Yeah. Also, it's easier to do it when you're actually writing on paper than with Expo marker because it's more detailed. So you guys, as long as you guys get the idea, that's the important part. And then the last one was 1.5. So that's a little bit right here. Okay. connect these. That. So the last one was this group right here. It had a 1.5 chemical shift and 6 protons, and it was a doublet. So this is right here is at 3, and it's a doublet. So we want about 2 peaks that are about 3 hydrogen length. So I'm going to do, oops, that's not good. Let me draw it and I'll show you. Again, it's kind of clustered, but if you look and see, I did 6 hydrogens right over here, around 1.5, because 2 doublet peaks that are on the same height as this 3 would equal about 6. And then I have this chemical shift in this one. So this is what it would look like roughly. Obviously, this is not exactly the best, but you can kind of see what it would look like. That's kind of dark. So that's how you draw it. If I go back to the shared screen now, are there any questions that you guys have if we're drawing this, or any? It seem pretty even. Okay. I'm gonna go back to shared screen now, and then.
So you should be able to do problems like that. You know, be able to isolate each proton and do exactly what Michaela's shown here for every group, and then ultimately put everything on the spectrum.
Yes. Okay, so I'm gonna skip through this. Okay, so this was the one that I looked up on the line. So you can see it's kind of similar to what I drew, but obviously theirs looks a little bit better because it's actually a computer system and it looks nicer. So the last thing that you can kind of do, or another technique, is you can use the NMR spectroscopy to distinguish between compounds that you usually couldn't. So this example, this is pulled from the book too. But if you look at all 3 of these compounds, all of them have aromatic rings and all of them have 2 methyl groups, making it kind of difficult, like if you were to use IR, because it would show the same types of groups and all this stuff like that. But with NMR, there's a lot of ways that we can distinguish between these compounds by specifically looking for those chemical shift, integration, and multiplicity values, because they're all going to be a little bit different. I think.
Hey, Mikhail, I want to say something about that.
Mm-hmm.
The leftmost is an orthoxylene, the middle one is a metaxylene, and the last one is a paraxylene. So some of your unknown compounds, you will have like ortho compounds, meta and para. So do you have the spectra for these, Michaela?
I don't. They were just given. This is just given in the book.
Okay. So
but you could like think of ways that they would be different. Like you could.
Yeah. Like the neighboring protons, will be different. So that's how you can tell if it is a ortho, meta, or para. So you can look at the first one, look at the colors. I think you have to talk to them about that.
So the colors signify what groups are equivalent protons. So like these methyl groups will both be the same, these hydrogens will both be the same, and these ones will be the same.
So how many peaks then will that spectrum have, the ortho? How many?
So this one will have 3.
3, yeah.
3 separate. And then this one, you can see that this hydrogen is different from this one because it's near the methyl groups. So this one's going to have 4 different peaks. Yeah. And then this one is only going to have 2 because all of these are the same. They're all next to a methyl group. So this one only has 2 peaks. So just looking at these, you don't even have to find all the specific values. You can just see that how many peaks they're going to have, and then look at the NMR and distinguish what compound is which.
And the splitting pattern will help as well.
Yeah, it's a good,
Okay. So one more second. Look at this, the ortho compound again. The hydrogen that is blue or green or whatever. How many neighbors does it have? See, it has 3 hydrogens on top and then 1 yellow hydrogen on the bottom. So you would see a total of 4 neighbors. So that could be part of the complex splitting. You see that?
Are you talking about splitting with?
Yeah, because they have neighbors on both sides.
Okay. Yeah. Anything else you want me to say?
You'll not see a whole lot of these, but you could. But definitely, I know some of your unknown compounds have patterns like that. That's what I wanted. Okay. Yeah, you're good.
Okay. So this is just kind of an example, back to like what the last slide was talking about. So both of these compounds are pretty similar. Like just looking at them, they both have this carbonyl group or an ester, and then they both have 2 methyl groups. But if you look at this, we could again use NMR to distinguish between these compounds. So since we kind of already went through how to find the chemical shifts, multiplicity, integration, the book already gives you, I think, all the answers to these, and we can talk about the differences when I show you that slide. So here we'll go to this one. So just looking at this slide, you can see that they, of course, they have 4 signals, or both of them have 4 signals. But whenever we look at the individual values, that's where we see a lot of the differences. So like multiplicity wise, this has, let's see what they have. So the chemical shift, it looks like the multiplicity and integration values are pretty similar, but the chemical shifts are what is different. So like here we have 2.2.
Yeah, the chemical shifts are slightly different.
Yeah.
For some, but the multiplicity, you know, the splitting is definitely different.
Yeah. So again, I don't have it drawn out. You could go through and draw these out, but if you just look at these values, you can kind of already tell enough. Like, for example, let's think of one. So
can you start with the one that's on the left and start at the top and go around, if you don't mind?
Go around, like describe why each of them is the way they are.
Yeah.
So this one is these 2 hydrogens are grouped together because they're both alpha to this carbonyl group. So again, they're 2 hydrogens though, so it's going to be that methylene one. I don't remember what the chemical shift value is, but it'll add a little bit more. I think, what is it? I mean, I don't think I have a chart with me.
No, that's okay. Don't worry about the chemical shift, but the split.
But it'll be a little bit higher than what it is because of this shifting it upwards. And it's also going to be a triplet because there's 2 neighboring protons right there. There's no hydrogens in this one. This next one is a 1.4. Is that the value of what it is? Of what a methylene is?
I think they've added everything. They've done the calculations. So that's what the total is. Yeah. If I remember right.
So this one, as you can see, it has 2 hydrogens in its group, and then it's a triplet as well because there's 2 neighboring protons. You might be curious why these ones aren't included, but again, it's looking at this carbon, not at these 2 carbons right there. So that's why it's a triplet, because only these 2 hydrogens are exactly like neighboring to this group right there. And then this methyl group. So if we look at that, it has a shift value of 1.0, and it has 6 hydrogens because there's 6 hydrogens total in the group. And it's a singlet because if we go 1 carbon away, there's no hydrogens. There's no neighboring hydrogens, meaning it'll just be 1 peak. And then this one is next to the oxygen of the ester, so that shifts its value up a little bit more. There's 2 hydrogens in the group, and also it's a singlet because there are no neighboring hydrogens. If we go 1 over, there's no hydrogens there, and if we go 1 over, there's no hydrogens there.
Go through the bonds to find out what the neighbors are, because when I look at it, like those 2 hydrogens, the last ones, looks like there are 6 neighbors, you know, but that's far away. So make sure that you go through the bonds and figure out what your adjacent carbons are, and figure out if there are hydrogens right there.
And just making sure you're only going 1 carbon away, because you could get confused.
Yeah.
That's for the most part how they got those values. But again, you could do something very similar with all of these. And then once you actually draw the spectrum, I think it would probably make more sense to how they're different too. So that would be, if you can't compare them numerically, you could do that visually through the spectrum.
Any questions about this? Because you'll be drawing some things like this, like you will actually come up with the individual boxes, you know, with of information. It's not hard, but it's just being careful.
Yep. Okay, so now this one, I think this part's a little bit more trickier than the other part. This one is being able to just look at a spectrum, which I think you guys had to do this for your post lab. So probably this will be pretty familiar to you. But looking at it and being
They
able to
have
see
not
how-
done their post lab yet. So
Oh, you have not done your post lab. Well, this will help you with your post lab because this is exactly what you're going to be doing. So you're going to be looking at a spectrum, and then they'll give you usually like the chemical formula. So like, I don't know, C6H10, blah, blah, blah. And then you have to be able to figure out the exact like chemical structure and how everything's like joined together. So the 4 main steps to doing this is first calculating the hydrogen deficiency index, which is your HDI. Did you guys already have somebody talk about this?
Yeah, Adele did, and that's from the previous chapter, I think. Yeah.
Yes. Okay. And then after that, you're going to consider the number of signals and integration of each signal. Then you want to analyze each signal and draw fragments accordingly. And we'll go through all these steps one by one. And then based on the shift integration multiplicity, that's how you assemble the fragments. And then you put all the fragments together to create that one structure that matches the molecular formula that you got. So again, this is just kind of a review, I guess, over HDI because it's been a little bit. So this is just your measure of unsaturation. So if it's 0, that means there's no rings or pi bonds. If it's 1, that means there could be 1 ring or 1 pi bond. And if it's 4, it doesn't mean it's an aromatic ring, but it means that it's likely that it has one. Because an aromatic ring, again, it has the ring and then it has the 3 bonds in it. So that's why it's 4. So this is kind of helpful to look at to see what is present in the molecule. And you can calculate it using this formula, or there's another way I think you can do it. It's like, I think it's, what is it? C, I don't know, C something.
Yeah, I think Adele went over that. And so you may want to refer to that section in the PowerPoint analysis.
Yeah, so you can use the formula.
Just a second. Hutch, is this your example as well? Oh, is yours different?
Go to the next slide.
Oh, I have like 3. There's like 3 examples on this slide. So
okay.
Let me.
Yeah. So if you have 3 examples, then we can skip this one if Hutch has.
Yeah, we can skip this one.
Let's see.
What's the next one? Yeah, he doesn't have that.
Okay, you want me to do this one?
Yeah.
Okay, that's fine.
Right, Hutch? Right?
Right. I don't have that one.
Oh, good.
Okay.
So the examples are coming, and even for your post lab, I forgot to mention, I'll do that on the announcement. I'd like you to calculate the HDI before you analyze your NMR, okay? For your post lab as well, but I'll post it. So you need to know how to calculate HDI.
Okay. Yeah, so the HDI, this one just uses the formula. It's always right. So if you can't remember the other way, that's totally fine. So first, they just start off, you get this formula right here. And then you also have your NMR spectrum that has all the integration values. So if we look for the HDI, that's where we use that formula. So it's 2 times the number of carbons plus 2 plus 0. I think that means there's no nitrogens. Minus 10, minus 0, because there's, I can't remember what the last part is. But the formula, I can look it up.
Can you put the formula?
Yeah, I have to get out the PowerPoint, and then I can.
Okay. So they can.
Why is my computer?
Review how to do that.
Yeah, it won't let me get out of it. I don't know why.
Just say the formula to them. They'll write it down, and we'll see if they can calculate the HDI.
I mean, I don't have the formula memorized. I have to look it up.
No, I saw it on the PowerPoint.
Yeah, I know. I'm trying to
but
get.
But you're not going to. Okay.
But my PowerPoint wasn't letting me go. Okay, now it is. Okay, so the formula is HDI.
Please write down the formula.
Equals 2 carbons plus 2 plus nitrogens minus hydrogens minus X. X is like the fluorine.
So nitrogen means the number of nitrogens, right? Carbon means the number of carbons. Hydrogen means the number of hydrogens in the formula, and X is the halogen.
Yep.
Okay. So if you have a formula of C8.
Yep. So our formula was, let me go back to it. I think it was this one. Yeah. Okay, so our formula was C8H10 oxo. So this is what we would get if we plug in all the numbers. You should see if it matches up with whenever you plug it into the formula that I just gave you.
Twice the number of carbons, +2, +0 because there are no nitrogens, right?
Mm-hmm.
-10.
There's 10 hydrogens.
10 hydrogens, -0 because there are no halogens.
No halogens. Yep.
What about the oxygen?
It doesn't.
Huh? Oxygen because you assume it's an OH and you don't.
Mm-hmm.
Yeah, ignore. Okay.
Yep.
All right. Everybody okay? Ladies and gentlemen?
Ladies. Okay, so then if with this formula we got wait, do you have a question? I don't know. Okay.
No.
Oh, okay. Good. So we have a HDI of 4. So what does this tell us? This tells us that there could be, we don't know for sure, but there could be an aromatic ring present, or there could be a lot of double bonds and or rings, but we'll just kind of see how it goes. But it gives us a good hint of what there could be. So now we take the integration values. So I can do this on my whiteboard if you want me to. This one shows all the work, but if we go back, it might make more sense. So for calculating the integration values, you take the lowest value on the graph, and that's what you divide everything else by. So the lowest value is 9.1. So we would take 45.1 and divide that by 9.1, 18.6 and divide it by 9.1, 19.1 divided by 9.1, and 9.1. So, and the reason we do that is because it shows us the integration values. So here's all the work kind of displayed right there. Again, whenever you do this though, sometimes you'll get weird values like 2.079, I don't know, whatever. Just kind of round it off to the whole number because you can't have like 2.4 of a hydrogen. So like in this one, she had 2.1, or I had 2.1, and it's 2 is close enough.
But if it is like 2.5, then you multiply the whole thing by 2.
Yeah, so whenever after you divide by all the values, you get your ratio, which is 1 to 2 to 2 to 5. And if we look, or if we remember our original formula, it had 10 hydrogens present. So all of these values add up to 10, showing that we don't need to multiply by anything. We have accounted for all of our hydrogens that are present on the NMR spectrum. So that's a good way to check and see whether you need to multiply these values by anything.
It's true. Yeah.
Yeah.
Did y'all get that? If the ratio, like, can you go back, please?
Yeah, I don't know why I went forward.
That's okay. So if you add up, there's 1 proton of one type, and then 2 of another type, 2 of a different type, and then 5. So that's 5 plus 2 plus 2 plus 1, that's 10. So that's in the formula, you have 10 hydrogens. So you don't have to multiply by another factor, okay? So that's another hint.
Yeah. So after that, we've figured out how many hydrogens are present, and we figured out what the HDI is. It's about taking each peak separately and analyzing that. So we're going to do this first. We're going to do this signal right before 2 ppm. It might be better if I just get out of this so I can go back easily. So we're going to do this one. I think that's the first one that she does. Okay. Yeah. So we're going to first look at this one over here. So looking at this, it's a singlet. So there's no neighboring hydrogens in that one. See how there's only 1 peak. Also, whenever we divided it by 9.1, it had a value of 1, meaning that there's only 1 proton present. Yeah. And remember, alcohol has that really weird range of values. So I kind of put like alcohol. It could be an alcohol. It seems like it would make the most sense. But again, that's kind of like where you can look at the other values and see if it would make sense with it. But we'll just kind of keep that. What I usually do whenever I work these, like on the whiteboard, is I will write out like, so here, I'll show you kind of what I do. So 2 ppm. Singlet, and then what is it, 1H. So I would kind of like draw something like this. Oh, I don't know if you can see this. But on for each like chemical shift that you're working, so that way you write down all the information that you have, and then you kind of like put what fragment that you think it could be. So that way you can like, then for the next signal, I would do the same thing. I'd write out what the chemical shift is, what the multiplicity is, and what the integration is, and then write that fragment over there. So that would be our first fragment. For the next one, we're looking at the signal slightly before 3 ppm. So that's this one. We're just going in order. And then this one, we found that it had an integration value of 2. So 2 hydrogens. And then also it is a triplet. If you look, you can see that there's 2 peaks and then there's that one that's in the middle. So that means, remember it's the n+1 rule. So that means there's only 2 neighboring protons present.
Michaela,
Mhm.
Could you put the actual spectrum up and then show it on your board for each peak? I think that might work better.
You mean like draw the spectrum?
Not draw the spectrum.
Mm-hmm.
Or copy, no, I mean, keep the spectrum like this on the side, and then you go on the board and
Sure, I can do that.
Yeah.
Yeah. Okay, so the next one's around like 3 p.m. So I'll show you guys this after I write it out. And then it's a triplet. And when we divided it by 9.1, it showed us 2 hydrogens. So if we look at this, this is all the information that I've gathered now for that second peak, or for this peak right here.
Can you see that, or how should we make that better?
I do not know. I can hold it up.
Okay.
Wow, this is great.
Should you go off the share and show that?
Let me try moving my room.
You can, if you click on your little window thing on the right, there's a button that lets you shift between the sharing and Michaela. So you can just click it.
Where's that at?
So like, if you go to where you have all the people, right?
Yeah.
And then you choose, there's like 4 options, and then there's this little thing on the right. There's like a big white square with a little black square.
I'm able to see Jamie on my screen now. So
Yeah, click on that. You can shift between the sharing computing and then whoever's talking with that.
I don't know what's going on, man.
okay, now we see you nice and big. And you can see your PowerPoint on the side. So, I mean, I'm able to see that.
You
Exactly,
can?
that's what I mean.
Yeah.
Just click on that.
Okay,
And-
we'll do that.
Okay, this is good because I can magnify the spectrum as well. So the first one that you have is the one around 2 ppm. And
Yes.
because it's a singlet, and because the OH can be anywhere between 2 and 5, you picked that to be the OH, okay? So that's temporary evaluation.
Yes, and this is, it's all about guessing what fragments you think. What was the question?
And then the second one, second peak, right?
Mm-hmm.
Second peak, is that the one at 19 point, I mean at around 3?
Yep. Oh yeah, around 3. Oops, yeah. Yeah.
Around 3, and that's a triplet. And then that has 2 hydrogens from the integration.
Yep.
Now, what do you think that is? Possibly a CH2, right?
Mm-hmm. Yeah. So with that, what I would do is I would just draw out like CH. Man, this marker's running out. So I'm kind of like looking like, here's my fragment. This like squiggly line just means like it connects to something else. So I know that that's like another methylene group over there.
So your window is reflecting. That's okay. Shining light.
Oh, sorry.
I want the group to tell me if you're okay, if you have any questions, because now's the time.
Yeah. I can't see everyone else.
I was just curious about the integration values. Like whenever you multiply them out, and then is it always like, okay, so say you get 1.53 and then you multiply it by 2. And then when you multiply it by 2 and you add both of them up, you don't get the number of hydrogens that you should have. So then what do you do? Does that make sense?
So you get like 1.5.
So somebody was saying that whenever you add up all the integration values, like the ratio, the 1 to 2 to 2 to 5, whatever, you add them up, and then you get the 10, which is how many hydrogens you have according to the molecular formula.
Yeah.
So if you add that up and you don't get that number, then is it wrong?
I would say
Possibly wrong,
yeah, it
but
should be wrong, I think. I mean, usually it works out. Was there an example where it wasn't working out or something?
No, I was just thinking about it. What happens if you don't? So like, especially like whenever you divide them up, right? You divide all the numbers divided by the little number, and then like you have to multiply them out because you get like 1.5 or 1.4 or whatever. So, and then whenever after you multiply them out, you add them up, and then you don't get that number. So then what happens?
So like usually, I don't know. Like,
again?
if I was, let's say I was looking at this one. So let's say that it was like C20 for some reason. So usually you can kind of tell like if I was to add all these up and I was getting 10, even though all of these are like the right numbers, I would know I need to multiply them by 2. So you kind of like look at your total. So like if your total was, I don't know, if your total is supposed to be 17 and you ended up getting 16, maybe you need to check one of your answers and see which one needs to be rounded off. Or like if the value's like, if you're supposed to, like for this one, if I was supposed to get 20 and ended up getting 10, then I know I need to double it. Usually it ends up like working out though. Or you kind of like figure out whenever you multiply it. Like you're not going to get 1.5 hydrogens as one of your integral values.
Right.
You know, like it's,
you're going to be saying like after you multiply them, because I think like the first option was to multiply by 2, right?
Yeah.
Especially when you get 1.5 as a result.
Yeah, I mean, you can, yeah, sometimes it'll be 2, sometimes it'll be 3, sometimes multiply it by like some other value. It really just depends whatever gets you like integral values, or I mean integer values, not integral. So
okay. There could be exceptions, but if there are, then you should let us know. But 90% of the time it should work. Especially the problems in your textbook and the problems on tests, there would be no exceptions like that. But if you were to go in a lab and do something, that's possible.
Right.
Okay?
Yeah. Okay. Are we doing, we're doing the other one. Okay. So let me go back to this
next peak.
Okay. So the next peak that we're going to do is this one right around 4. Or a little bit before 4. So again, I would just probably grab my piece of paper and write out what I know about it. So I know that this one is about like, I'm going to say 3.8 ppm. It's all just estimate. It looks like, I don't really know what it is. I think it's a triplet.
It's a triplet, yeah.
It's a triplet. And then when we did the integral values, it came out as 2. So we know it's 2 hydrogens. So looking at this one, it looks pretty similar to the other one. The only difference is that
shifted further down.
Yeah, the shifted values. So I'm gonna again think that this could be a methylene group. So I'm just gonna kind of draw it out. So you can kind of see it in the bottom there. I did it on the bottom. So there's all my fragments so far that I think I have. So then we're gonna do that last one. So the last one that we have, here, I'll draw it out. So we have a chemical value of 7.3, I guess.
Now, this is another thing. Just like alcohol is between 2 and 5, aldehydes, hydrogen is around 10. If you see anything between 6 and 7, what is this one? What's the integration?
Let's see what they put. They put around like 7. As long as
7, yeah. Between, you know, like around 7, between 6 and 7, it's likely to be an aromatic ring. So you need to make a note of that. Okay?
Yeah, you can kind of already tell there's a lot of peaks on this one. It's kind of hard to distinguish. It looks like maybe 5. I don't know. Yeah, 5. There we go. 5.
Well, it should be 6 if there are 5 protons. No, I'm sorry.
Here they just put multiplet.
Yeah.
Which that's a good thing to put too whenever, usually like for like this thing, you can kind of see how the signals are both even. But for this one, we see a lot of signals that are just kind of like all over the place on height. So a multiplet is a good way to describe it. And then whenever we did the integration values, this is the one that had 6 because 45.1 divided by 9. So we know that there's 6 hydrogens, or no, 5. It was 5. Sorry, I can't do math. 5 hydrogens that are present in this one. And so if we look at all that we have, we don't really have any double bonds or rings yet. And if we look at that chart, it would make sense for this to be a ring because it contains the right amount of hydrogens. And it also has the multiplet showing that there could be neighboring hydrogens, and the chemical shift value is good. So for
the
this
multiplet for the around 7 ppm, that's because the hydrogens within the ring, they split each other. So it's a complex splitting within the hydrogens of the aromatic ring. That's why, that's one of the reasons why you get a multiplet.
And the other important thing to look at, here I'll go back to the thing, is that it had an integral value of 5 hydrogens. So this shows that there's probably 5 hydrogens that are present, and then there's only one thing that's connected to whatever else is on the structure. So this is important because you know that there's only one area. It's not like if there was like 4 hydrogens, then you know that there's 2 regions that need to be added on, but because it was 5, that's why we know that it's going to kind of be like this, and it's going to be something else connected.
So it's a mono-substituted ring. So you'll have a, right? Yeah. And if you have 4 hydrogens, then it's likely to be a di-substituted ring.
Yeah. So then the next thing to do is just kind of pair all these together and see if it would match up with the structure and what values you're getting on this graph. So I'll show you what the structure looks like. So whenever you put it all together, it should be like this. And again, it's kind of like guess and check, like see where things fit the best. So obviously, like this oxygen is terminal. I forgot to draw the other end of these. So yeah, this alcohol group is terminal. That means it has to end here. And this one's also terminal because it only has one area where it can connect. So I know that these methyl groups have to be in the middle, which you can see that that's how we put it in the structure. So they have this ring on one end and then the alcohol group on the other end with the methyl groups in between. So that's kind of important because you can see where things are supposed to go.
And also, if you look at the splitting for CH2, they split each other. So each CH2 does not have anything else on the other side, just a CH2. So that's why each CH2 is a triplet.
Yeah.
Because where it connects to the benzene ring, there's no hydrogen, right?
Yes. And also the chemical shift values, we detected earlier that they were a little bit higher than what they should have been. But now we can see the CH2 next to this alcohol and this, or alpha to the alcohol, and this one beta to the alcohol is what causes those values to be a lot higher, which makes sense with what we previously found. It has the right number of carbons and hydrogens, and it has 1 oxygen. So this matches up pretty well to the whole NMR spectrum and the formula. And so that's how we know that that's the structure that it could be. Is that kind of, any questions about that? Or I'll go back to the thing.
Please ask questions because you'll be doing something like this for your post-lab. It's not hard, but it's just, you know, you have to look at every detail and especially piecing together, you know, it's like a puzzle. Yeah. So you have your individual fragments, and then you have to keep the splitting pattern in mind when you put it all together. Don't forget that, because you can go back and check your own answer. See if you can tell if the splitting is correct and if the positioning of the groups on the on the spectrum looks fine. Does it match up with the chemical shift values that it's supposed to have from the table, and so on.
Yeah. Yeah. Are there any, you can also type them in the chat, I guess, too. I can check. I don't know where that is.
Yeah, any questions?
Oh.
They're all peachy.
Yeah,
We
it
have
gets.
another,
I think it gets easier too when you practice it.
yeah, and
This is
they
a lot
have
of
the
these.
recordings and they have the PowerPoint.
Mm-hmm.
Do you have another example or is that it?
I do. I didn't know if you wanted Hutch to do his or if
Yeah,
I
I think Hutch can, right, Hutch?
Yeah, mine's very similar to that. So
Okay. So, um,
this
it's
is the
very,
other one that I have.
okay, why don't you finish yours, Michaela, then?
Okay. So we'll just do this last one. This is we're gonna do the same process I'm gonna make myself the big screen. Okay. So this is the same thing that we were doing earlier. So first we're gonna calculate the HDI. So that's using that formula that you guys wrote down earlier and that was in the presentation. So we have 2 times 10 because there's 10 carbons, plus 2, that's just in the formula, plus 0 because there's 0 nitrogens, minus 14 because there's 14 hydrogens, and then minus 0 because there's no halogens, divided by 2, gives us a HDI of 4. So this means that there, again, could be an aromatic ring present. So now we're going to take all the, I think this one already gives us the hydrogen values. Yeah, so with this one, they already give us the integral values. So some of the NMR spectrums will do that. You don't have to divide by them. So this is common to see. So again, we already have our ratio set up, how many hydrogens are on each peak, and this equals 14, which matches up with our total number of protons that we have there. So that's a good sign. So now I'm going to go, I'll erase this, and then we're going to go through and analyze each signal again, and get each fragment. So, what is it? Okay, so first we're going to do the signal between 1 and 2. I'm sorry, I can't really see it very well. So that's this one right there. If we're looking at this, it has 9 hydrogens, and I think, is that a singlet? I can't really tell.
Which one? The one at, yeah, that's,
Yes. Yeah. So this is a singlet, and this is one of the ones that Dr. Mary was talking about earlier.
and Hutch
I mean,
did too.
there's like, yeah, there's the isopropyl one, what is the terbutyl, and then I think there's the third one. So if we look at this, we can kind of already tell what it's going to be because it's one of those rare like signals. So I'm going to write out what the chemical shift value is. It's like probably 1.4, and it's a singlet with 9 hydrogens.
That's me, sorry.
That's okay. And then, so this one is, since it has 9 hydrogens, it shows us that it probably could be a terbutyl. So I'm going to draw that out. And that's just one of those ones that you kind of have to like recognize. Like in the textbooks, those 3 common ones are just good to know whenever you see them, like that probably is a terbutyl because it's not affected by anything. So as you can see by the board, I just kind of drew it out. I put the chemical shift, what it is, and the hydrogen amount, and then have my little fragment there. The next one that we're doing is the one, I think we do around 5. Yeah, around 5. So with this one, we have a little peak right there. So here, I'll separate this out.
There's
So
only
we
one oxygen, so it's probably an OH group.
Mhm.
You have 2
Yeah.
oxygens, it could be a carboxyl group or an ester.
Yeah. And because there's also, I don't think there's any other signals that are above, like showing up
10.
the other hydrogen groups, then we're basically good. So I'll show that. Okay. And then the other signal is we have one that's right before 7. So that last one, it has a chemical shift value of like 6.8. And then it looks like it's a doublet. I think it's a doublet. Right. Let's see what they put. Yeah. So it should be a doublet. And then also has 2 hydrogens. So the doublet shows that there's 1 neighboring hydrogen, and it's also around a value of 7. So this could be part of the aromatic ring. So remember also if the aromatic ring could have multiple signals if the hydrogens are not equivalent. So like a while ago, whenever I showed you guys that one slide or whatever that had, these three things, you can see how even an aromatic ring will have different signals depending on the hydrogens and where they are. So when looking at this, we can see that, oh, wrong one. Oh, wrong problem. Oh, I have to find it now. Okay, yeah. So we can see that it's probably going to be part of the aromatic ring, but it's not accounting for all the hydrogens. So then the last one that we have is this signal right here, which again is also in the aromatic region. So it's above 7, probably like 7.3 or something like that. And it looks like it's also a doublet and that it has 2 hydrogens. So we analyze that last signal. Again, it shows that it's in the aromatic region, but it only has 2 protons and 1 neighboring hydrogen present, making that part of the aromatic ring. Okay, so now it's about analyzing each signal. So again, I told you that there were 2 signals that were probably present for the aromatic ring. So there's 2 sets of protons recorded. One set of protons is shifted more than the other. So one of those was like a little bit higher than 7. Therefore, 2 different compounds must be attached to the ring, showing that it's probably di-substituted. Because if we combine this information with this information that had 2 hydrogens, or here, I'll go back to the spectrum. There were 2 hydrogens here, and then there were 2 hydrogens there. We add those up, that's 4. And the ring has 6 spots. So that means that there's 2 areas where it could be substituted. And then we only have 2 other groups. There's only the tert-butyl group with the 9 hydrogens, and then the alcohol group. So obviously, if it's di-substituted, the only important thing that we have to figure out is where the groups are positioned on the ring. So if we look here, since these hydrogens have to be equivalent and these ones are equivalent, we know that both of the groups are going to be placed across from each other. Because if we did it in a different way, then the hydrogens, these hydrogens wouldn't be equivalent and these ones wouldn't be equivalent. So that's kind of, I went through that one a little bit faster since we did an example. But if you look at these, that's the way to pair up all the signals and again, just test it out. You kind of have to like get the group separately and then just pair them up in the best way. So, yep. Okay, that was kind of fast. Do you guys have questions about that one or any other things you want me to go over?
Do you want that thing to be reviewed or are you okay?
I was just wondering if like this could be uploaded to Canvas so that we can
Yeah,
look over it.
I'm recording.
I could do that.
No, the PowerPoint is uploaded, John.
Okay.
And I'm recording the session, if that's what you're asking.
Okay.
Yeah, the PowerPoints are uploaded for Hutch's and Michaela's in the lecture Canvas course shell, and I'm recording the session. So does that help? Okay. So Hutch, do you want to review yours quickly and then we can close shop?
Sure.
Okay. Thanks,
Okay,
Michaela.
I'm gonna
Stop sharing, right?
Yeah. However, okay, I'm gonna stop sharing. So we're good. And I will not pin me anymore.
You want what?
I was pinned. I was the main person.
Oh, yeah.
I will not pin myself.
She pinned herself on the wall.
Yeah.
Okay, so my example is really similar to the first one she did. And whereas the molecular formula is almost identical. But here's the NMR spectrum, and you can see the integration values here. So first I calculated the HDI. So 9 carbons times 2 plus 2, no nitrogens, minus 10 hydrogens, and there's no halogens. Divided by 2, I get 5 as my HDI. And like she said before, anything 4 and up, it's consistent with an aromatic ring. So just kind of keep that in mind. And then I took the integration values to get the integration numbers. So 10.2 is my smallest one, and I divided all the others by 10.2. And since the values that I got, they could easily be rounded up or down. So I didn't need to multiply these numbers by 2 to get whole numbers. I could easily just round them down because they're so close. So I got a ratio of 1, 5, 2, 2. So 1, 5, 2, and 2. So now we're going to analyze each peak like she did with hers. And we're going to start with the first one upfield, which will be this one. So that's better. So we're going to analyze these two right here first. And so these are common with the methylene group because there's 2 protons present in each of them. And the splitting, there's 3 peaks, so there's 2 neighboring protons affecting each of them. So therefore, we could think of this as 2 methylene groups put together. So a methylene group bonded to a methylene group. And you can see it here. And according to where methylene groups should be, it's not consistent on where they should be, but it's a little bit downfield, which means that there could be a functional group in the compound that's causing it to shift. And next we're gonna analyze this peak right here. And notice that the peak is around 7 ppm. And like she said before, peaks around there, they're consistent with aromatic rings. And since the HDI was above 4, we can go ahead and say that this is consistent with an aromatic ring. And due to the fact that there's 5 of these protons, we can say that it's monosubstituted. And then the last signal, like I said before, earlier in my presentation before, singlets around 10 show an aldehyde. So we can go ahead and say this peak shows an aldehyde or a proton connected to an aldehyde. So with all this information gathered, we can show each of the predicted fragments of the compound. And from here, we can put it together to see what we can do. And luckily, they only go together one way. There's only one way to put it. And that is this way, where the aromatic ring, the benzene ring, and the aldehyde are both terminal, and the 2 methylene groups are in the middle, connected to both.
So a couple of things. The HDI was calculated to be 5, right?
Yes.
The aromatic ring, you can leave it on there. The aromatic ring accounts for 4. So if you have an HDI of 5, and then if you see a peak around 7, you know there's an aromatic ring, and then there's something else. And if you see the aldehyde at 10, so you know that's the carbonyl, so you have the unsaturation from the carbonyl. So you have, information from different sources that helps you complete the structure. And another thing, this was in, I think it was Michaela's first structure, and what Hutch has now, if you look at the two CH2s next to each other, they're next to each other, but on the left, there's no neighbor. On the right, there's no neighbor. So the splitting is just the CH2 getting split by the other CH2. So if you see those two CH2 peaks like that, can you go back to your spectrum, please?
Yes.
Thank you.
Right here?
See that? Yeah. So you see those two CH2s, and each has only a triplet. That's because they're isolated. So next to the CH2 on the right, you have the aldehyde, and next to the CH2 on the left, you have the benzene ring. So there are no neighbors coming in from both sides. So these are all clues, and the more problems you do, the more you will see these. And also, if you look at, did you finish that? Okay.
You want me to go back?
No, this is fine. So since you have your Canvas, Hutch, can you pull up the NMR table on your screen? You should go to Canvas, chapter 15.
Okay. Let me see.
Any questions about this example, students? Anything that you want to ask on the chat? Okay, so they're all good so far.
There we go.
Okay. Yeah, can you make that bigger, this table?
Okay.
This table will be given to you. And look at some of these values. You have the methyl, the methylene, the methine, and then the allylic hydrogen, the alkenyl, aromatic methyl, the aldehydes hydrogen. Now these are the ones below are very, very specific. Remember the alcohol, like a regular alcohol, it's 2 to 5. Don't go.
Okay.
I'm still reviewing that. Then the vinylic hydrogen, 4.5 to 6.5. The aromatic, the aryl, between 6.5 to 8. You see that? Aldehyde, approximately 10. Look at the last one. I didn't talk about it until now. The carboxylic OH, although it's an OH, but this OH is next to the carbonyl group. So it's shifted even further. So that's 12. So if you have an alcohol group, an carboxylic acid, you'll have 2 hydrogens, and you'll see that OH way at the other end. Okay, so those are hints. So always use the table and do not isolate your information. You have to make sure that every piece of information given is, working in harmony. And only then you'll know that your structure is right. Can you move it up a little? And the one on the bottom, that's for the UV. The one on top, that will be given too, but without the example. Okay. So the table, the first one that we looked at, that's very, very useful for getting the structure from a spectrum given. Okay. I think we've done a lot of examples, and I will post the recordings as well. And with this, you should be able to do your post lab. I'm going to give you till Thursday to do the post lab. Is that a good idea? Yes or no? Or
works for me.
Works for you? Okay. So if you have any questions, you may want to ask Michaela or myself, and we'll be able to help you. and fill the sheets as you do your NMR problems, and then I'm going to modify it. And for each unknown, the first thing you'd have to do is calculate the HDI. Okay. And then analyze like how Hutch analyzed and how Michaela had shown to analyze. Use that method. Just be systematic. Everything will work out fine. Okay.
Where are those sheets again?
If you go to the lecture, I posted it in the lab as well. If you go to the lecture canvas, and then where I think everybody should go look. I'm not able to share my, have you stopped sharing, Hutch? I think you did.
Yes, I stopped sharing.
Okay, all right. Let me see. I don't know why I'm not able to share my PowerPoint. Maybe I should keep it open. Let me try. It's not letting me share my PowerPoint, but go to the Canvas lecture.
Mm-hmm.
And then go to chapter 15. It should be on top. I think the ones that we are doing currently, I moved it up to the top.
Okay.
Do you see it? Do you see chapter 15? Do you see NMR tables? And then
where
I said
it says post lab.
Complete analysis in the worksheet.
Uh-huh.
Okay. And then in there, I'm going to include the calculation of HDI for each unknown.
Okay.
Right?
So if we print this out right now, is it okay if we just like do the HDI at the bottom?
Do it first for each.
Okay.
Because that'll help you with the analysis. You see that?
Right. But since there's not like.
Oh yeah. You can show it on the bottom. Yeah.
Okay.
I understand. Yeah. And then you see Hutch's PowerPoint and Michaela's PowerPoint. And then the recording, I think I should stop recording now because we've answered those questions. Otherwise, those files are too huge. Stop.